Okay, today our last section here, Unit 4, is redox reactions. And a few of these redox reactions, like the ones we're going to talk about today, are often too complex to balance the way that you would normally traditionally balance chemical equations. So we have to come up with a method that will allow us to still be able to balance these. And what we're going to do, we're going to break the reaction into its two components. The item that's getting oxidized and the item that's getting reduced. And then try to balance each of those individually. So basically all we're doing is breaking this up into smaller parts. And that's a pretty common problem solving technique in a lot of different classes that you might have. Trying to make things more simple by breaking it up into little parts. Okay, so before we get into that, here are a list. This is a very incomplete list, but this is just some common types of items that you might be able to see in oxidation reduction reactions. The one thing that's not listed in any of these, or not often in here, well, I guess it is. I was going to say elementals, but there's some elementals. So those would be elementals. Whoops, not halides. Halogens would be the elemental in that case. Okay, so there are some elementals here, but otherwise some kind of common items, some common threads. Nitrogen compounds, chromium compounds, manganese compounds, sulfur compounds. Are those the only ones? No, but those would be a couple that you might see over time. And then also we're going to have to kind of visit this. Some of these say that the reaction only occurs in acid. That means that you need other things in the beaker, in the test tube, wherever you carry out this reaction, and it would have to be carried out in an acidic condition. And what's that going to mean? When you're all done with the balancing, you'll find that there's hydronium, H positive or H3O positive in there somewhere. If it says it has to be carried out in basic solution, you're going to find somewhere in that chemical reaction some hydroxide. And it's going to be not something that's going to change oxidation states, but it's going to be there to allow everything else that is supposed to change oxidation states to do that. You're going to go back later and look at these when you want to start practicing these on your own. I am going to go through a sample question that's already done, and I'm going to address these bullet points. And by the way, I am starting at the top. We could actually call this part 1, and then keep on going down until we got to the end. Okay. Again, you can visit these on your own after you want to try to do these for yourself. This is definitely going to require you to practice. Just by watching me is not going to be quite enough for these questions, that's for sure. Okay, so you might have a homework question or a textbook question or a test question, so forth, that would start off with that. And some people call this a skeleton reaction. And it has the components that are important, but it doesn't have everything to balance the chemical equation. So I don't know if you noticed, but both of those two items that I arrowed there have a common atom. And then these two have a common atom. And we're going to pull those out, and one of those is going to be involved with oxidation, and one's going to be involved with reduction. And we can, before we start, figure out which one was which. oxidation or reduction. But actually, I think we can actually wait until we're almost finished with this and then come back and revisit which one was actually oxidation and reduction. So we pulled the I minus going to I2 out. Did we have to do that one first? No, we could have done this one first. So you can only do one at a time. So SeO3 minus 2 going to Se. Basically, you have to pull both those out. So I'm going to erase all those things I just put down there so this doesn't get so busy. Okay, so I'm going to just look at the reduction first. Okay, so it says balance the S's and I's because that's one of our first steps in that process, that slide that I had before. So there's one Se on the left, one Se on the right. So that's good. Okay, don't worry about the I's. I'm going to go back and we'll visit the oxidation column after I'm all done with the reduction column. Okay, so the next role is to balance oxygens with waters. So I have 3 oxygens on the left, so I would need 3 waters on the right. Okay, so basically those blues, the blue shaded are what I'm adding to the steps here. Okay, part 3, add H's, balance H's, sorry, with H positives. So I had a total of 3 times 2, 6 H's on the right, so I need 6 H's on the left. Next, balance charges with electrons. And we've done this already before, balancing charges with electrons. On this side, we have a total of 0 charge. We have a minus 2, a plus 6. So if we have 4 negatives, 4 electrons, that would balance that out. On both sides, they would have a charge of 0. It will not always work out that both sides have a charge of 0. Okay, so now we are done. No, we didn't do step 5 yet, but we are done up to this point. That is a balanced half reaction. Now, let's figure out why it was a reduction. Electrons are being gained. If they're on the reactant side, they're being gained. And so reduction involves gain of electrons. So therefore, this other one has to be oxidation, but we'll try to verify why it's oxidation. Okay, so I'm going to go back up to the top and step 1 through step 4 now with the oxidation column. So balance SEs, well, there are no SEs there, but there is an I. So that's why we need the 2. Balance oxygens. Well, there's no oxygens in the compound, so I don't have to worry about that. Balance H's with H positives. Well, there are no H's in this either, so oftentimes you're not going to do every one of these steps. Part 4, balance charges with electrons. Well, I have a minus 2 over here, so I would need a minus 2 over here. Okay, so now at this point, we have 2 half reactions that are complete. Also, we have now proved that this is oxidation because 2 electrons are lost. They're on the product side. So oxidation involves the loss of electrons. Lastly, what we would want to be able to do is add the reduction and add the oxidation back into collectively one chemical reaction. But electrons have to be fully transferred, meaning that if you lose 4, you got to gain 4. If you lost 2, you got to gain 2. Whatever the number is of lost, it has to be the same as the gained. So right now we have 4 that are gained, but only 2 that are lost. So we are going to multiply that entire half reaction, the oxidation, by 2. So the 2 coefficient became a 4, the 1 coefficient became a 2, and the 2 coefficient became a 4. And now we can take all the reactants and add them all together. Reactant, 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 reactant. Add those all together and put them on the reactant side. And if you've noticed, the electrons didn't quite make it there. We'll have to figure out why. And then we have product, product, and product, and product. And I'm going to add all those on the product side. And the electrons didn't show up there either because I had 4 electrons and I had 4 electrons. Well, they will cancel on both sides because they are identical. If we had any other items that were identical, they would also get crossed out. Now we have a balanced chemical equation. And I think you'd be hard-pressed to be able to go straight from there to this without going through all those steps. If you can do it without the steps, hats off. But I'm going to recommend that you use this half reaction method. Okay, so let's give one of these a shot. Again, remember, you can't do both at the same time. So we have the iron component. Move that up a little bit. And to get this to balance, we would have to add 1 electron. So therefore, this is the oxidation half reaction. So we have the other component, the dichromate, going to chromium +3. We have to balance the chromiums. They're balanced. Balance oxygens with waters. Balance hydrogens with H pluses. And then balance charges. Over on this side, I'm going to erase this in a second, but we have a +6 charge. So over here, when it's all said and done, we better have a +6 charge. So a +14, a -2, that would give us a +12. Well, I want to get to a +6. So if I would add 6 electrons, would that work? Let's see. 6, it's a -6, and a 14, and a -2. I think that would give us a +6. So that works. Okay, now we would like to be able to put both these half reactions. Oh, by the way, electrons over here on the reactant side means this is the reduction half reaction. Okay, so now to put these together, we need all the electrons to cancel. 6 electrons on the reactant side do not cancel with 1 electron on the product side. But if we multiply this entire half reaction by 6, that will work. So 6Fe + 2. Any other reactants? Yep, we have on the reduction half reaction, we have some more reactants. Whoops. And that makes a couple different products here. And that should be balanced. If you go through and look at every one of those atoms, that should balance out. Okay, and let's talk about this now for a second. We haven't visited this idea. It happens in acidic solution. Is there something in there that kind of makes it look like it's an acidic solution? Those H positives. Doesn't matter how many, but it's H positive means in acidic conditions. Okay, definitely you must practice these to get good at them. You can't just watch. Well, this one's going to be interesting. This one says it's going to be basic. So when we're all done, we're going to have one more step. So let's break this up. We have the I- going to I2. I think we're going to need a 2 there and a 2 there. I guess that means that that is oxidation. And the reason I'm using those oxidation reduction isn't to help us balance these, but often you're going to have another part of the question that's going to say something about what's being oxidized or what's being reduced, something like that. Okay, so then we have permanganate and manganese dioxide. The manganeses are already balanced. I think we're going to have to use 2 waters to balance the oxygens. We'll need 4 hydrogens for H positive, 4 H positives to balance that. And then I think we're going to need 3 electrons. And you might need to go like this to make sure you separate the 2 half reactions so you don't get them confused. 2 electrons will not cancel with 3 electrons. So we're going to multiply this entire half reaction by 3, and we'll multiply this entire reaction by 2. That way, I was thinking about common denominator there. So 2 times 3 is 6, 3 times 2 is 6, so 6 electrons will cancel. So let's write that out. We have 6I minus. Do we have any other products on the other half reaction? Yes, we have 8 H positives. We have 2 MnO4 minuses. We have 3 I2 product. Any other products? Yeah, we have 2 MnO2s and 4 waters. That looks like it's in acidic conditions. But we're not allowed to have it in acidic conditions. We need it to be in basic conditions. So how could we, does that mean I screwed up? No, didn't screw up. I just have an additional step now. So what I'm going to do is where the H positives were, I'm going to think about neutralizing those. But I can't, I need to still think about the law of conservation of mass. So if I decide to use something on this left side, I would have to use something also on the right side. So what I'm going to do, actually let's just stay with the red there. What would happen if I added 8 OH minuses? Remember, and I did say, so let's go and add those in. What would happen if I added 8 H positives plus 8 OH minuses? It would equal 8 H2Os. So we had 8 H positives. We added 8 OH minuses to both sides. So now on the left-hand side, we no longer have those starting amounts. We have now 8 waters. But we're not quite done because we just created these waters, but there were some waters over here. So I think we can lose 4 waters on both sides. And that got a little busy there, so I'm going to rewrite the entire item. And we're going to check out, is it still balanced? And unfortunately, you can easily, just as I could easily lose an item along the way, miscount something along the way. And once you have that, you might have to go back closer to the beginning to figure out what you need to do. So let's make sure that's balanced. Again, like I said, it's easy to kind of lose your accounting here. So let's look at iodines. I have 6 iodines on the left. I have 3 times 2, 6 iodines on the right. Hydrogens, I have 4 times 2, 8 hydrogens on the left. I have 8 H's on the right, that's balanced. Oxygens, I have 4 and 8 more, 2 times 4 for the permanganate, so that's a total of 12. And I have 2 times 2 for the manganese dioxide, and then 8 more in the hydroxide, that's a total of 12. The manganese, 2 on the left, 2 on the right. So all of our atoms are balanced, but let's double check charges. We have a -6, we have a -2, so that's going to give you a -8, and then over here we have a whoops, I don't know why I put electrons there. We have a -8 over there. So charges also balance. So that's good. Now lastly, is it in basic conditions? So for basic conditions, we need something to represent base somewhere in this chemical reaction, and there it is, the hydroxide. So I think it's fairly easy to know the rules, but it's more difficult to follow the rules, and it's more difficult to not lose your place with accounting there. So you need to practice these a couple before I think you're going to be proficient.